Something flattened the tops before the ranges finished becoming mountains. The strange part is not that one peak is flat. It's that flat summits show up on every continent, in ranges built by different forces, at different times, under different climates. The second problem is the line work. From satellite maps, ridgelines, escarpments, terraces, and abrupt benches often look less like chaos and more like cuts. And the third problem is institutional. The USGS, national surveys, and university papers all describe pieces of this, but almost no one explains the full pattern in one place. If you stay with this idea long enough, it starts to pull on everything else. The official explanation is both true and strangely incomplete. Entire mountain systems preserve old flat surfaces high above sea level, and the phrase, cut marks, survives not because someone literally sliced the earth, but because the planet keeps displaying scars that standard explanations describe separately and rarely connect. The familiar story comes first. Mountains rise through tectonic collision, volcanic buildup, crustal uplift, and faulting. Then wind, rivers, glaciers, freeze-thaw cycles, and gravity wear them down. That part is not controversial. The Andes, Appalachians, Drakensberg, Deccan, the Colorado Plateau, the Highlands of Scotland, all of them fit pieces of that model. The data is not in dispute. It's the conclusion that no one can settle. What makes this uneasy is the contradiction. Mountains are supposed to be symbols of vertical violence, compression, uplift, chaos. But again and again, when you look at real topographic profiles, relief maps, and horizon photographs, what remains are level crowns, table-like remnants, parallel benches, and long planar surfaces that seem to remember a flatter world. That is where the hidden theory begins. Not with fantasy machines. Not with a lost civilization dragging blades across continents. With a serious geological possibility that sounds less dramatic and is, in some ways, more unsettling. Many mountain ranges contain the remains of ancient low-relief landscapes, planation surfaces, erosional surfaces, peneplains, uplifted plateaus, marine-cut benches, lava-capped mesas, glacially truncated shoulders. In other words, some of the world's mountain tops were once not mountain tops at all. They were surfaces. Broad ones. Ancient ones. Then the land moved. The reason people call them cut marks starts with what the eye sees before the textbook arrives. A range in profile. Flat, then broken. Flat, then broken. One summit matches another across miles of relief. Benches step down a valley wall like giant machine passes. Escarpments run for astonishing distances with abrupt edges sharp enough to look intentional. In satellite imagery, lineaments cut across terrain in ways that feel engineered. The human brain sees a blade. Geology sees process. The question is whether the process has been explained in a way that matches the scale of what's visible. Take Mesa Country in the American West. Monument Valley. The Grand Staircase. The high plateaus around Utah and Arizona. The official explanation is layered rock exposed by erosion. Hard caprock protects the top. Softer material erodes below. Isolated buttes and mesas remain. That is solid geology. So the flat top itself is not a mystery there. It is a remnant surface protected by a resistant layer. But that only closes one problem and opens another. If that logic works so cleanly in one place, why do we see versions of the same geometry in very different rock systems, including volcanic provinces, folded mountains, and ancient shields? For a moment, there is comfort in that. A mesa is not a cut mountain. It is a surviving piece of a larger surface. Fine. But here is where it gets strange. Move to the Appalachians. Old mountains. Deeply eroded. Not dramatic like the Himalaya, but geologically more revealing because time has had longer to work. The ridges are worn. The relief is softened. And yet geomorphologists have spent more than a century arguing over ancient erosion surfaces preserved across the eastern United States, high-level surfaces, intermediate surfaces, valley-side benches, summit accordances. Accordance is the word that matters. It means different summits seem to line up, as if they were once part of a broader level landscape. Not proof of cutting. Proof of memory. USGS papers, state survey reports, and geomorphology texts have long treated these surfaces as clues to uplift history. A once lower landscape gets raised. Rivers cut down. Fragments of the old surface survive as flat or gently rounded high points. Later viewers see the surviving fragments and ask the obvious question: why do the peaks line up? The mainstream answer is not dramatic. Because they were once connected by a surface that has since been dissected. That answer is strong. But it also means something the public is rarely told clearly. Some mountain ranges are not just piles pushed upward. They are the wreckage of older plains lifted into the sky. Now add volcanic provinces to everything I just told you. The Deccan Traps in India. The Columbia River basalts in the northwestern United States. Layer upon layer of flood basalt spread out over enormous areas, later carved into steps, cliffs, benches, and flat-topped remnants. From a distance, many of these landscapes look cut, stacked, or sheared. And the official explanation, again, is real. Repeated lava outpourings built broad level surfaces. Later erosion incised them. There is no mystery there until you widen the scale. Because when you widen the scale, the same visual language repeats across unrelated systems. Lava plateaus. Sedimentary mesas. Glacially planed highlands. Marine terraces. Fault-bounded uplifts. Ancient peneplains. Different causes. Same image. Flat crowns. Sharp breaks. Level remnants. Long edges. That is why the cut marks idea never quite dies. The pattern does not disappear. But this is also the point where the argument usually jumps too far. A flat peak becomes evidence of intervention. A ridgeline becomes a blade mark. That is where the theory collapses. The Earth has more ways to make a straight-looking edge than intuition allows. Fault scarps can run for miles. Glacial truncation can produce severe profiles. Differential erosion can leave abrupt benches. Lava flows can freeze broad horizons into place. Marine erosion can cut terraces with startling regularity. If you ignore those mechanisms, the whole case fails. So why does the unease remain even after you accept all of that? Because the official explanation is often delivered as a list of isolated mechanisms, while the eye is seeing a planetary pattern. When geomorphologists talk to each other, they use precise categories. Peneplain, peneplain, summit accordance, structural bench, erosion surface, paleosurface, truncated spur, marine platform, planation surface. Each term captures a local process. But outside that specialist language, the public gets a much flatter message. Mountains rose, erosion happened, case closed. That summary leaves out the part that actually feels impossible. Entire regions may have been worn down close to level over immense spans of time, then lifted, tilted, faulted, flooded by basalt, or carved apart. In plain English, some of the world's most dramatic high places may be the broken leftovers of surfaces that were once far less dramatic. When later uplift exposes them, they look cut because, in a sense, they were planed, just not by a machine. By time, water, chemistry, ice, and tectonics acting in sequence across durations the human mind barely handles. And that creates a bigger problem. If a surface can be ancient, then buried, then lifted, then preserved only in fragments across separate peaks. How often are we looking at mountain ranges and misreading them entirely? Not in detail. In category. Now add glaciation. In many ranges, glaciers did not just carve valleys. They truncated spurs, shaved shoulders, widened passes, and cut cirques that leave unervingly geometric forms behind. The Alps, the Rockies, the Southern Alps of New Zealand, Scandinavia, glacial landscapes often look edited, cleaned, reduced. In some high plateaus and old shields, ice also interacted with older erosion surfaces, preserving or exposing flatter remnants. The mainstream explanation is fair here. Glaciers are powerful enough to produce shapes that feel artificial. So one major source of the so-called cut marks is not hidden at all. It is glacial truncation layered onto older topography. But glaciers do not explain the flat summits in hot, dry, or tropical systems where similar summit accordances still appear. That is the next contradiction. Shift from pure geology to mapping. Open a global relief map and start marking flat or nearly flat high surfaces. Southern Africa, Brazil's highlands, Australia's tablelands, Ethiopia, Arabia, the tepuis of South America, the plateaus of Tibet, the dissected uplands of North America, the Scottish Highlands, the Canary Islands. The pattern is not that every mountain is flat on top. That would be false. The pattern is that flat or gently accordant summit surfaces are so widespread that they stop feeling local. They look like remnants of repeated episodes in Earth history when leveling happened on scales far beyond any single valley. That is where institutional discomfort enters. Not conspiracy. Inertia. Geology is specialized for good reason. A volcanologist studies volcanic provinces. A structural geologist studies faults and folds. A glacial geomorphologist studies ice-shaped landforms. A sedimentologist studies layers. A geodesist measures uplift. Each one can explain part of the picture. What almost never happens in public is a clear synthesis of why the same visual signal, flatness at elevation, keeps appearing across all of them. And when no one tells that full story, other people will. Usually badly. That is why cut mark survives as a phrase. It is crude. It is misleading. But it is trying to describe a real visual fact. The Earth preserves old surfaces in broken pieces, and the breaks between those pieces can look violent, sudden, and unfinished. There is also a time problem buried underneath this. Many of the surfaces in question are older than the mountains we associate them with in their current form. The surface may come first. The mountain, as we know it, comes later. A peneplain can form, then the crust lifts. A lava plain can spread, then rivers dissect it. A marine platform can emerge, then faulting can elevate it. A plateau can be incised until isolated flat tops remain like memory chips in the terrain. So the main mystery closes here. The flat peaks are not evidence that someone cut every mountain range with a lost machine. They are evidence that many mountain ranges preserve fragments of older level surfaces later raised, fractured, capped, or carved into relief. That sounds like the mystery is over. It isn't. Because that answer resolves the mechanism, not the scale. And the scale is what still disturbs people. How long does it take to plane a continent-sized region close to level? How stable must climate and base level be? How many times has the crust risen, stalled, and risen again? Why do some surfaces survive almost intact while others vanish? Why do satellite images of certain escarpments still look shockingly abrupt if the explanation is slow erosion? These are not fringe questions. They sit inside mainstream geomorphology. They just rarely reach the public in a form that feels coherent. Now move from science to perception. When most people hear erosion, they imagine soft rounding. A stream. A canyon. A cliff slowly crumbling. What they do not imagine is erosion producing vast, near-level surfaces over millions of years, then tectonics lifting those surfaces thousands of feet, then newer erosion slicing them into isolated table peaks and ridgetop alignments. That sequence is real. But because it is difficult to visualize, the brain rejects it and reaches for the simpler image. Something cut this. That is not stupidity. It is a scale failure. And one more thing. Some of the most viral examples used to sell the cut mountain idea are mixed cases. A single landscape may show structural bedding, ancient planation, fault scarps, lava caps, and later glacial or river incision all at once. Different processes stacked on the same terrain can create forms that feel over-explained or under-explained depending on how they're presented. A tourist hears one sentence. A specialist sees 5 overprinted histories. The gap between those two views is where suspicion grows. What remains, then, is not a hidden machine but a hidden timeline. The top of a mountain may be older than the mountain. The edge may be younger than the surface behind it. The valley may be youngest of all. What looks like one event is often a sequence separated by tens of millions of years. The cut mark was never explained because it was never one cut. It was a stack of episodes mistaken for a single gesture. So why does this matter now? Because we are entering an era of planetary imaging precise enough to expose these surfaces everywhere. LiDAR, global elevation models, satellite radar, high-resolution relief mapping. The more clearly we map the Earth, the more obvious these giant accordant remnants become. And the more obvious they become, the more dangerous lazy explanations get, both the official kind that compresses everything into erosion and the fringe kind that compresses everything into someone cut it. The truth is harder, which is usually how truth behaves. Here is the final reframing. Every mountain range on Earth does not have flat peaks in the literal sense. But nearly every continent preserves mountain or highland surfaces that are flat enough, aligned enough, or abrupt enough to force the same question. What are we really looking at? Not just rock. Not just uplift. Not just erosion. We are looking at landscape memory. Ancient surfaces broken, lifted, and stranded high above the levels where they formed. The cut marks were explained, but only in fragments, scattered across specialties, hidden behind technical language, and almost never assembled into one clean public narrative. And that opens the next question. If the Earth can preserve old surfaces inside modern mountains for tens of millions of years, what other features have we been misreading simply because we are looking at the final shape and not the sequence that built it? The real question is not whether the theory sounds strange. It's whether anyone has shown you the full chain of processes with the scale and clarity it deserves. Because once you understand that some peaks were once plains, some cliffs were once edges of level worlds, and some so-called cuts are really the surviving geometry of vanished surfaces, the planet looks less random than before. And much older.